In this video, we close up our discussion of oxidizers by talking about some more common oxidizers involving some heavy-duty kinds of oxidation, and then closing our discussion by looking at the chemistry of matches. So we're going to start with looking at some sodium compounds, in particular sodium permanganate and potassium permanganate. Now, permanganates are pretty heavy-duty oxidizers. They're um, among the more reactive oxidizers that we have. And the primary reason for that is right here. We've got manganese in a very high oxidation state, a +7 state. And high oxidation states with metals are quite often associated with reactivity, and in particular with oxidizing power. And so we see that here. Now, where do we see permanganates used? Well, we can see them used for dermatitis, either bacterial or fungal conditions of the skin. We also know that concentrated solutions of these have been known to remove matter from biological and chemical processes by oxidizing them. Now, in addition to permanganates, we also need to look at nitrates and nitrites because, again, these are very common. Among these, we can see that the nitrates are only used as oxidizing agents. The nitrogen in nitrates are in the +5 state, and there's really not any more room for the nitrogens to go in that range, so they only act as oxidizing agents. For nitrites, we see the nitrogen in the +3 state, which means it can go to the +5, it can be reduced, it can be oxidized, or it can go the other way to a more reduced state and act as a pretty good oxidizing agent. And where we see these primarily, I mean, nitrates come out in a couple of different places. One of them is gunpowder. Nitrites we see often in different types of preservatives. Nitrates and nitrites are both used in preservative kinds of ways because of their oxidizing or reducing powers. And so when bacteria come into contact with them, they basically get oxidized by the nitrite or the nitrate, and that is what helps preserve it. And so we see this used a lot in meats, especially processed meats. Nitrates and nitrites are often added to those as a preservative measure for that reason. Next thing we want to look at are peroxides and superoxides. Now, we talked a little bit about peroxides already. In particular, we talked about sodium peroxide and calcium peroxide in one of our previous videos. Now, superoxides are in the same kind of vein. The only difference between them is that instead of carrying a -2 charge, we've got that oxygen to oxygen single bond that only has an associated -1 charge. Now, both of these, because of that oxygen-oxygen single bond, like we talked about when we talked about peroxides in general in a previous video, we know that these are highly reactive because of that instability in that bond there. And so these are thermally unstable substances. When we put them into water, they react with water quite vigorously. And so as a result, we need to store them in some moisture-proof containers to keep them from interacting with water. The last kind of miscellaneous group that we're going to look at are the persulfates. Now, persulfates or peroxydisulfates, depending upon what you want to look at and how you want to call them, have a similar structure to what we saw in the peroxides. We're talking about a sulfur to sulfur single bond with bonds out to the other side, to either side, with a -2 charge. Now, peroxydisulfates or persulfates, however you want to look at them, are highly corrosive solutions. They are thermally unstable. Where we see them used the most often are in the computer industry. We use them as a stripping agent of sorts. The major danger with persulfates is that we're going to see pretty nasty kinds of reactions. They're highly corrosive. They're thermally unstable. They just they're not good playmates usually. Um, the last thing we want to talk about out of this chapter are matches. Now, matches come into two different forms. There are the strike anywhere matches, and then there are safety matches. Strike anywhere matches are, well, as they said, they can be struck on any surface. Safety matches are the ones that we're the most familiar with. They're the ones that have the strikers on the box or on the back of the matchbook, and we have to strike the match against that surface in order to get them to light. Now, in either case, the DOT regulates their transportation as flammable solids, so class 4 materials. When they are the type that cannot spontaneously ignite or undergo decomposition when subjected to 8 consecutive hours of 200-degree temperatures or greater. And that's a really important thing because, again, a lot of the rules that we put in for transportation are based upon kind of what if scenarios. What if a truck breaks down in a really hot climate and is carrying flammable goods? How dangerous is that going to be? What kinds of issues are we going to be calling in that scenario? And so that's where this is coming in is if we have 8 hours of this stuff at 200 degrees Fahrenheit, are the matches going to stay unlit? That's the important part. Now, going into the two dimensions here, strike anywhere matches, what we have is a mixture here of tetraphosphorus trisulfide, sulfur, lead 4 oxide, powdered glass, and glue. And it is the powdered glass component right here that is what allows it to be a strike anywhere. This is your rough surface. So the main purpose of the box or the back of the matchbook on safety matches is providing that rough surface on against which we can strike the match head and it will cause the reaction to go. The lead 4 oxide, this is going to be acting as your oxidizer. And then the phosphorus and sulfur compounds are going to be acting as your fuel. By contrast, safety matches, they don't have the glass on them. And so as a result, you need to strike it against a friction surface to provide the necessary energy to kickstart the reaction. What we see without that glass, we see a slightly different oxidizing agent. We see the potassium chlorate being used in most cases. We also see a slightly different fuel. Most safety matches use antimony sulfide instead of phosphorus, in addition to obviously the sulfur that is held in both. And the reason for that is the phosphorus and the powdered glass, which were on the match head in the strike anywhere matches, notice that both of them now are on that striking surface, which is one of the reasons why the striking surfaces usually appear red, especially on the big boxes of matches, because of that red phosphorus. So we've got ourselves a fuel, we got ourselves an oxidizer, and we got ourselves a rough surface to strike it against. And so just to kind of summarize and put it into context, we've talked about the idea of the flame triangle or the flame tetrahedron. Here are each of those for each match. So for the strike anywhere match, we can see that in our strike anywhere match, we have the decomposition of lead oxide to oxygen to form the oxidizer. We've got the sulfur, the phosphorus sulfide compound, the paraffin wax that is used to kind of hold it together, and the wood, that is the stick itself, that is the fuel. And then the heat comes from the friction of striking that match against that rough surface and activating the phosphorus and the lead oxide compound. By contrast, the safety match, we have potassium chlorate acting as the oxidizer to provide the oxygen for the fire. We have the antimony compound, the paraffin in the wood, providing the fuel, and then the red phosphorus and the chlorate and the friction, that's what's going to provide the heat to get the match to ignite. So the chemistry of matches is actually kind of cool. You can see that phosphorus compounds and sulfur compounds are always going to be involved in it. The oxidizer can vary, and depending upon what the natural use is, where we find that powdered glass, where we find that excess phosphorus, to jumpstart the reaction, it's either found on the match head itself, in the case of a strike enabler match, or on the striking surface of the matchbook or the matchbox in a safety match. So this concludes for us our look at Chapter 11, the chemistry of oxidizers. Our next chapter, and actually the last chapter that we are going to cover in this course, concerns the chemistry of some polymer materials. And so that'll be a really exciting chapter to look at because there's a lot of really cool chemistry and a lot of cool consumer products that are polymer based. So I'm looking forward to that. Until then, have a good day.